Here's an example of a well-studied material, especially in the microlithography arena. It's called SU8. It's an epoxy-based material. And you can basically see a bunch of trenches that are manufactured under different thermal conditions. You change the temperature of baking, you increase the cross-linking density. These gaps that you see over here are roughly in the order of about 2 to 5 microns. And you can see that the there can be a lot of distortion depending upon changes in temperature. This is captured in this plot of the height of the material at different locations as a function of cross-linking temperature, bake temperature in this case, seen in this particular research article. So you can see that height, aspect ratio are strongly dependent upon the process temperature, and in this case, that affects the cross-link density. If precision is important in the prototype or in the product, then paying attention to the degree of cross-linking and how to manipulate that to achieve target dimensions is an important attribute to pay attention to. Compared to thermal cross-linking, you can have the cross-link density change as a function of UV exposure, UV wavelength, UV exposure time, and then also time for thermal cross-linking. So these are all some ways in which you can affect precision of the structures that you're 3D printing. So this is evident from this study. Softer baking leads to better SU8 structures in terms of having greater stability, right, based on these plateau regions. In this plot, you have from another article, you have stress versus strain for materials that have initially been exposed to a UV dose of 1 joule per square centimeter. When you in that as exposed case state, you have a very high strain possible in the material, highly elastomeric material. As you begin to change the baking temperature, and you have two different conditions, 95 degrees and 200 degrees centigrade. So when depending upon the thermal exposure, you end up transforming from an elastomeric material to a more brittle material as seen in the stress strain plot. Also, if you increase the time for the reaction at a given temperature, as you go from 5 minutes to 30 minutes, you end up making a more brittle material. And if you go from a low temperature curing reaction to a higher temperature curing reaction over here, from changing from 95C to 200C, you end up getting the most brittle material, a material with the highest cross-link density. So this is an example of effect of cross-linking on mechanical properties. In that article, this is another representation of not only the strength and the modulus on opposite axes, but also the elongation as shown over here on the right of your screen in terms of the y-axis. You can see that as you increase the cure time, you end up making a stronger material. But what happens is that you also have a plateau effect. Your elongation begins to decrease. This is also represented over here that we saw in the earlier plot. Here's an example of what happens as a function of changing cure temperature as you keep increasing that. You have modulus plotted on the left axis in the y direction and strength and elongation now plotted in the right y-axis. You can see the material becomes stronger as you increase the temperature for curing, and also elongation begins to come down, make a more brittle material as you increase the overall temperature. In addition to these mechanical property changes, the color can change as well, and so the appearance of the product can change. What about UV dose? Because we've seen that UV exposure and the intensity that can change cross-linking density. And you see some things that are in parallel to what you saw with time and temperature effects. You end up getting a stronger material. You do end up having some improvement in elongation, as it turns out, compared to lower UV doses up to a certain limit. So this gives you a different kind of a trend with photochemical transformation compared to just using time and temperature. What about the glass transition temperature? We said that that could be something that changes with cross-link density. So monitoring the glass transition temperature changes as a function of curing conditions allows us to follow extent of reaction. And you can see that glass transition ends up increasing, you end up getting a more brittle material that tracks with the mechanical properties changes, and there is a plateauing effect. This glass transition temperature can be measured by differential scanning calorimetry. We saw a version of that when we were looking at one of the research articles in module 1, and we'll look at some more of those aspects as we explore research article in module 2. And here you can see that basic reaction exotherms change with different curing conditions. Accordingly, glass transition temperatures and the endotherms related to that change as well for the cured material. So to summarize, what we have is when you begin to make tests immediately after processing, depending upon exposure time and exposure temperature, you end up having changes in mechanical properties. But if you test the same product after a day, you end up having, on a reference basis, a slight reduction in properties. That implies that products made from reactive polymers tend to not be as stable, and that should be taken into account in employing 3D printing with certain materials made from reactive polymers. And one of the challenges then in 3D printing with reactive polymers is how to increase the stability of properties, mechanical properties and others, including color, optical clarity, and so on, as a function of time to make durable goods.